Hello everybody, and welcome to example 5 on page 76. This is going to be our first example of finding the inverse of a linear transformation. This is going to walk us through it, the process step by step. Okay, so let's read this together. Let t from p2 of r to p2 of r be a linear transformation defined by this formula. T of p of x is p of x plus 2p prime of x. And let beta be the standard ordered basis on p2 of r. Okay, and the first thing they'd like us to do is to find a matrix for t relative to that standard basis. Okay, we know how to do this. We just need to substitute in our basis vectors one at a time. So t of 1, t of x, and t of x squared. Okay, and remember that the formula for the transformation is sitting here. So to do t of 1, we're going to get 1 plus 2 times the derivative of 1. I'm just following what that formula tells us. So 1 plus 2 times the derivative of 1 is 0. We're just going to get 1 out of that. Okay, and then similarly for x, if we substitute x in for p of x, we're going to get x plus 2 times the derivative of x, which is 1. Okay, rewrite that and it becomes 2 plus x. And then t of x squared would be x squared plus 2 times the derivative of x squared, which is 2x. Simplify that, and we're going to get 4x plus x squared. Okay, so what does our matrix look like? Okay, well, looking at our first output, 1, we can write 1 as 1 plus 0x plus 0x squared. So that would give us a 1, 0, 0 in our first column. Then we come to 2 plus x, that's 2 plus 1x plus 0x squared. So that would be 2, 1, 0. And 4x plus x squared, let's see, that's 0 plus 4x plus 1x squared. So that's going to give us a 0, 4, and a 1. Okay, so there's our matrix, and that's our answer to part A. Okay, so let's see what part B is asking us for. So they'd like us to first find the inverse of the matrix T beta, which we calculated in part A, and then to use it to find a formula for T inverse. Okay, so it's this T inverse that we're really after. What the directions are suggesting to us is that we can figure out the inverse of our transformation over here by first finding the inverse of the matrix that we found in part A. Okay, so this is going to take us back to some review from previous linear algebra courses. There's a process for finding the inverse of a matrix that we're going to review down here. Okay, now space is a little tight here, so I'm going to try to write small. Okay, so I'm going to go way over to the left margin here and start by writing down the matrix that they gave us, or I'm sorry, that we found in part A. And what we're going to do is to augment the identity matrix. Okay, so 1, 0, 0, 0, 1, 0, and 0, 0, 1. And here's what we need to do. You might remember this when I say it. What we'd like to do is to do row reduction so that the matrix that we see over here becomes the identity matrix. If we do that, then the matrix that winds up on the right-hand side will be our inverse. That's the way this works. This process is called Gauss-Jordan elimination that we're going to do. Okay, so we want to make the matrix on the left look like the identity. Notice that we're already off to kind of a good start. We've got zeros in the lower 3 positions. It's kind of already in an echelon form. So what we need to do is to get zeros where the 2 and the 4 are. Okay, that will make the matrix on the left look like the identity. And the question is, what row operations do we need to do to make that happen? All right, well, kind of the first thing that we would like is to get a 0 in this position, in the 4. Okay, and if you think about it, we can do that by taking negative 4 times the third row plus the second row. That's the row operation that we're going to do. All right, so I'm going to start by recopying the third row here. 0, 0, 1, 0, 0, 1, and then we'll do that row operation, negative 4r3 plus r2. Okay, so looking back at the matrix on the very left, we're going to take negative 4 times 0 plus 0. That's going to give us a 0 there. Okay, and then moving back to the matrix on the left again, negative 4 times 0 plus 1 is going to give us a 1 here. Okay, and then negative 4 times 1 plus that 4, that will give us the 0 that we wanted. Okay, and then negative 4 times 0 plus 0, that's still 0. Everything's 0. Okay, and then negative 4 times 0 plus 1, that's 1. And finally, negative 4 times 1 plus 0 is negative 4. Okay, so there's our new second row. All right, and finally, now we'd like to get a 0, looking back at the left matrix where that 2 is. Okay, so what row operation would do that for us? Okay, well, let me recopy it first. Okay, otherwise we're going to be trying to do too much here. So it's this 2 again that we want to replace and make 0. Okay, so how could we get that to be a 0? Well, if you think about it, we could do that by taking negative 2 times the second row and adding it to the first row. Okay, so we're done with the last 2 rows, so let's go ahead and just recopy those. 0, 1, 0, 0, 1, negative 4. All right, and now we'll do the row operation that we wrote down. Okay, so looking at the middle matrix, we're going to take negative 2 times 0 plus 1. That's going to give us a 1. Okay, then negative 2 times 1 plus 2, that's going to give us the 0 that we want. Okay, and I'll let you check the rest of these. Negative 2 times 0 plus 0 is 0. Negative 2 times 0 plus 1 is 1. Negative 2 times 1 is negative 2 plus 0, so we'll get a negative 2 there. And then finally, negative 2 times this negative 4 plus 0 is going to give us an 8 up here. All right, so notice a couple of things here then. Number 1, we've got the identity to the left. That's telling us that we're to the end of our elimination process here. And what that means is that this matrix over here to the right should be our inverse. Okay, so what we can say with confidence here then is that the inverse of t beta is 1, negative 2, 8, 0, 1, negative 4, and 0, 0, 1. Okay, so we've kind of completed the first part of this question, which asked us to find the inverse of t beta. Now the question is, how do we use that to figure out the inverse of our transformation? That's what we're really interested in here. And the key is to remember what a matrix does for us. It takes us from coordinates to coordinates. Okay, so what we will do then is to take this matrix, okay, this inverse that we just found, and we're going to multiply it by kind of a generic set of coordinates, A, B, C, and remind ourselves how we're thinking about those coordinates. Those represent beta coordinates of an input, okay, some polynomial that we're plugging in. Okay, now we can do that matrix calculation. So if we just do ordinary matrix multiplication here, we're going to get A minus 2B plus 8C, B minus 4C, oh, whoops, sorry. Let me try to write that a little bit more neatly for you here. Okay, and then finally the very last one is just going to give us a C. And what pops out here are beta coordinates of not P of x, but the inverse of P of x. T inverse of P of x, because after all, remember what this matrix does. It's a matrix for the inverse transformation. So what should come out are coordinates for the output of this inverse function. Okay, and what that gives us is a roadmap, a way to actually write down our formula for T inverse. We have T inverse of, okay, remember that A, B, and C represent coefficients on our basis, which is, I'm going to just superimpose that, it was the standard basis. So when we look at A, B, C, we're interpreting that as being A plus BX plus CX squared. Okay, and then similarly, the output, we're looking at these three numbers and interpreting those as coefficients on our basis. So we would get a minus 2b plus 8c times 1 plus b minus 4c times x plus c times x squared. Okay, let me try to rewrite that a little bit better. Okay, and what we're circling here, that is our formula for the inverse transformation. Okay, and in the next video, the next brief video, we will take a minute just to check that formula, convince ourselves that it's right.